Okay, good afternoon, guys. So, as you remember, in the rest of our class, we worked with neural networks, and this week we will talk about using TensorBoard and 1DB library for online tracking the training process and regularization of neural networks. And next week, we will talk about convolutional neural networks, which are used typically for images. And the week after, we will talk about recurrent neural networks, which are used for sequential data like time series, text, and audio. So, okay, the camera. So before we start, I want to show some tips about Homework 10. So in Homework 10, I asked you to build a neural network with one hidden layer, if I'm not mistaken, and use different activation functions. So then I asked you to plot the decision boundaries, and they will look something like that. If you want to use the built-in function for decision boundary, plot decision regions, you should create a wrapper class because the class for the input for this function should contain a function predict, a method predict. So I just want to show you an example how you can write this class. You can write this class which takes as input your model and has only one function, predict. Predict. In predict, you return the prediction. So your input is NumPy, for example. You cast to torch tensor, apply your model, and make a prediction, return the class label. And after that, you can use this function, this class, in this function, plot decision regions, instead of writing your own function to visualize these decision boundaries. And then you will see something like that. Different decision boundaries, depending on the different activation functions. So today we will talk about different activation functions. And why actually do we need the different activation functions? So let's look at our neural network. So this is how our neural network with one hidden layer looks like. We have inputs, we have linear layer or matrix just multiplication to change the dimension of our input. Then we apply a sigmoid activation function, and then we apply another linear layer. So the question is, why do we want to apply this activation function? Can we just apply linear layer after the first linear layer? So what do you think, guys? Why we can't just stack linear layers? Why we should also use non-linear functions in between? Yes, Ross?
Just doing a bunch of linear layers can just be reduced to one linear layer.
Yes, because if we use a linear function of a linear function, we will get again a linear function. And then there is no reason to use several layers, linear layers, because they are equivalent to one linear layer. So that's why in your models, after every linear layer, you should use non-linear function. And for now, we use only one nonlinear function, sigmoid function, but nobody uses this function in practice. So it's kind of historically the first function because there was this theorem that the linear combination of sigmoid functions can approximate an arbitrary function. But what is the problem? And this actually was the problem why neural networks were not popular in 90s because okay, let's answer this question why. Um, For now, you can just say because they were using sigmoid functions as activation functions. Um, so let's look at this sigmoid activation function. Of course, they all are implemented in Torch. So this is the expression, how it looks like, and here is the plot. What can you see from this plot? First of all, this function returns only positive values. It's range between 0 and 1. But what why this function actually uh, prevents our neural networks from learning? What's the problem for very small and very large values? Yeah,
They're approximately zero.
constant. And what is the derivative of the constant? 0. We update our weights using gradients. And if the gradients are 0, we won't update our weights. So our networks won't be learning. So this is the problem with sigmoid function. It has non-zero derivatives only in the proximity of the origin, but for larger values, um, this problem is called vanishing gradient problem. The gradient is vanishing. So the other function, very popular, is called hyperbolic tangent. Tangent hyperbolic. Um, so this is the formula. It uses exponents, and this is the plot. It looks like a sigmoid function. The only difference is that it can take also negative values because the range now is between -1 and 1. So if you want that your layer returns outputs of both sign, it's a good idea to use hyperbolic tangent function. Um, but again, it has the same problem. It goes very flat for large and small values. The function which is used in practice more frequently, do you know which function is used typically in neural networks as activation function? Uh,
Yes.
Yes, ReLU, rectifying linear unit. ReLU. And when people uh, used started using this function, then the neural network actually started training because now we don't have this problem for large values. So the formula is as maximum between 0 and x. It means that for positive values, it just coincides with y equals x, and for negative values, it's just 0. So yeah, it will have 0 derivatives for negative values, but for positive values, even for large values, it will have non-zero gradients. Um, but this function has also one, well, actually several problems. First of all, it's 0 for all negative values. And to fix that, you can use so-called leaky ReLU, leaky ReLU function. A leaky ReLU has pretty similar formula, x for positive values and negative slope times x for negative values. And it looks as follows. It's the same as ReLU for positive values, but it has a small positive slope because negative slope times negative value for negative values. Yeah, in this example, it's by default it's 0.1, but you can change this parameter in this function. You can indicate the slope 0.2 or whatever you want. And the second problem was that it is not differentiable at the origin. It's not really an issue because, in float calculations, we almost never get the precise number. So it's uh, um, very unlikely to get the exact zero with float computations. So it's not really an issue. But uh, to fix this angle, people introduced ELU, exponential linear unit. LU. Again, the formula is the same for positive values, x, but for negative values, there is an exponential function, and the plot looks as follows. So it has the smooth connection with line at the origin. And the other modification of this function is called SILU. SILU from sigmoid linear unit. So the formula for this activation function is very simple, just x times sigmoid. Because sigmoid takes values for large values 1, then it will behave as x for large values. For small values, sigmoid is close to 0. So for small values, it behaves as ReLU. But at the origin, the sigmoid function is different, is not 0. So it kind of creates this smoothing uh, region at the corner. And also, sigmoid function is nice for computation because derivative of sigmoid function is just sigmoid times 1 sigmoid. So, okay, and there are, I don't know how many, but I believe hundreds other activation functions because You can change many parameters, like you remember there was a parameter alpha here, so you can change these parameters. Uh, and uh, it just it's it's chosen by tries and errors. So, for example, if you find that one activation function works well for your data, then we use this function. For images, typically we use relu. For example, for mm, um, language models, they use modification of CLU. So just from practice, people decide which function is better for specific task. Okay, and in your homework, I ask you to build this one neural network with one hidden layer and try apply different activation functions, and you will see how it influences the decision boundary in the end. Okay, so next thing I want to talk about is using the tensor board for visualization of loss of your training process in your browser. For example, if you train your model on the server, you can't open images there, but you can get a link, URL link, and open this link in your browser, and you will see the training process, the loss function in real time. So you remember our problem from last week, the absolute value function. What this one? Yep. Um, I will use this as the example. Hello. So here is our data, and here's our and then neural network model. Here's missing one equal to sign. So we have the neural network with one hidden layer, uh, which goes from 1 to the hidden size and from hidden size to 1. And as you know, now we should use activation function between any linear layers, because otherwise there is no reason to use multiple linear layers. You can use just one. Um, and uh, also, okay, I can show on this example, instead of using applying each layer at a time, you can use a layer which is called sequential. And self sequential. And just list all the layers that you want to apply to your input. Here, it looks correct. And instead of using these several assignments, you can just apply sequential to your input, and it will actually apply sequentially this layers. So sometimes it's useful. You also can create a list of layers, but um, it won't work because mm, to create a list of layers, you should register these layers um, as trainable layers, and there is a uh, special type of list. What it's called? I don't remember. Um, so you can't use just a list of layers. You should use another uh, layer. Do you remember, Ben, how it's called now? Don't want.
Yeah, that I ran into that problem.
Oh, you ran into this problem? Yeah, yeah, yeah. Yes, yeah. So um, uh, list of layers in Torch. Okay. It just lists all the layers. Um, um, module list. There is a instead of list, you should use module list. Okay. So because for large neural networks, we want to repeat the layer multiple times, so you can use list comprehension like for, and then you should use module list instead of list uh, to make them kind of trainable. Um, uh, Trainable modules and also with different parameters instead of just repeating the same layer. Okay, so yeah, you can use sequential, hidden size 5, okay. Then MSE loss, optimizer, and training. So, and prediction. Okay, looks bad, looks good, not or bad, I don't know. So if you look at the loss function, for example, at first iterations, it looks oscillating. Let's use 50 maybe. So to get the more smooth uh, plot uh, that will represent the trend of your loss function, if it goes lower or higher, we can use so-called exponential smoothing. Last time we talked about this for optimization. So instead of plotting the current value of loss function, we will plot the current value of loss function multiplied by some constant plus the value of our loss function from the previous step. It's kind of inertia. So let's introduce another array, smooth loss. Mm. or history, okay. And I will initialize the first value by 0 because I need to use the previous value. And I will append. Okay, it looks good. Also, I will use some smoothing parameter alpha. And I will append the current value of loss function multiplied by, if alpha is 0.9, by 0.1, by a small, very small number. So I will take into account the current value with very small coefficient. Because if our new loss function value is large, we will multiply by small. And plus the previous value of loss function with high coefficient alpha. So it's uh, let's plot. So if I run this code, it will continue training. So I will reinitialize my model and train it again and plot history and smooth history. So you can see that the smooth loss function looks let's do 100. Has less as like small magnitude of oscillations. If I increase parameter and make it 99, uh, then it will be more smooth. And if I use smaller alpha, 0.5, for example, then it kind of just plots the current value of the loss function. So if you want to observe this loss function in real time, you can use the simplest tool, which is called tensor board. So let's import from Torch utils tensor board. Torch utils tensor board, import summary writer, and initialize this object summary writer. So when you initialize this object, so for now I have only one folder in the root. When I create this summary writer object, it will create another folder, runs, where it will store the information about your loss function and also the date and time. And now we also need to add the information about our loss function in this writer. So in our training loop, instead of using our history lists, we can, yeah, it looks correct. Writer add scalar. Then you use the name of your curve because you can use train loss, you can use validation loss. And here we store the epoch and the loss.item. And to visualize, again, if you do this on your, not in Colab, but in Python, uh, you will see just the URL address and you can copy this URL and open in your window. But in Colab, we use the we will visualize right inside the notebook. So to call it inside notebook, okay, what is the command? Load um, load external tensor board. Then we should indicate the folder with where this tensor board will read the data. Uh, tensor board. By default, this directory is called runs, but you can create another directory. And okay. It launches the tensor board, and for now it's empty. And let's use maybe more epochs. And initialize optimizer and run us and look at the tensor board. So you can see the training loss. If you want that it updates automatically, you can use reload data, for example, every 10 seconds. And let's see if it's still running. Okay. Then after 10 seconds, we should see the updated plot. Hmm. Right, it's not updating. Hmm. Okay. So, and you can run your model on the server and watch on your screen actually how the training process goes, like does loss go down or not? So maybe you should stop training and modify your model and so on. Okay. Let's stop training. And if you initialize your writer again, it will create um, a new folder. So if I will run training again, it will write in the new folder. And if you update, let's see, data couldn't be loaded. Maybe I should run this line again. Yeah, you'll see the results of training from 2 sessions, so you can choose just one or remove another one. Okay, so this is how you can use the built-in tensor board for um, ah, and aha. And also it has parameter smoothing. So if you set this parameter high, you will see more smooth trajectory, which represents the trend. If you set this low, it will be more noisy. So it's the same as we used alpha in our code above. So you can also change this smoothing parameter here. Okay, so the next and actually the last thing for today is how can we work with images, and we will create data set and data loader for MNIST data set. And we will train a model that recognizes the handwritten digits. And your next homework will be to train your model and test your model on your digits. I ask you to draw 3 digits and pass through your model. So hopefully it will recognize them correctly. But you shouldn't expect a good accuracy from this model because we are using fully connected layers. Next week, we will learn convolutional neural networks, which were developed specifically for two-dimensional objects like images. And so the last homework will be to build convolutional neural network and test your images. And in final project, again, you will use convolutional neural networks, but the data set will be larger. It will be data set of birds, and you will need to classify different species of birds. And the other project, I give you 2 projects to choose. You can choose one or another one. Will be with faces, but still images. So today I want to show you how to create a data loader which will read your images from your drive. Because when we talked about logistic regression, we used MNIST data set as a built-in data set from Escalon, I believe. So today we will upload real images and read them from the disk and convert into tensors in torch format. And so how you would work with a real life situation when you have raw data and you should create the tensors from this raw data. Okay, so I uploaded the starter code for this. So Torch has different libraries for different modalities. For audio, there is Torch Audio. For images, there is Torch Vision library. And from Torch Vision library today, I will use only one function, read image, um, which will read the image and transform this in Torch format, in PyTorch format. So it will return a tensor. You can use also other libraries, and we will talk about this next time, like Peel or OpenCV. When you read images with that libraries, they will return either their format, like Peel library, or NumPy array format. So torch vision returns the torch format, but it doesn't work with GIF format. So let's run these imports. Yeah, and by mhm. Till the end of the class, we will work mostly with notebooks because now we will have larger code and I will just upload prepared notebooks. So we will upload images from Kaggle. Unfortunately, it requires password, so I will just upload. So I couldn't do just Kaggle data set and name of data set. I tried that, but it asked for password. Um, I will just upload from Kaggle and upload on my collab. Because I have many files with name archive. I will choose the last one. And you can see it's not a large data set, pretty small. Um, okay. And rename because collab doesn't like the spaces. Oh, wait a second. I I uploaded it's in a different notebook. Let's see. Can I see this here? No, okay. I had to upload here. Okay. You're tired. I'm also tired. It's the last weeks of classes. Um, okay. Rename. And okay, now we should unzip our archive, and you can see that it contains just the images in standard format PNG, not the tensors, like when you upload Mini's data set from the built-in dataset class, it just returns tensors. I want you to show how to work with raw images. And yeah, you can see that it created the folder MNIST. It has train and validation subfolders. In train, we have 10 folders. And if you open a folder with label 0, you will see there are 50 files, and every file will contain a handwritten digit 0. Um, so this is how our data set looks like. And if we read, for example, image with torch vision, to visualize this image, we will use matplotlib image show, but because we use torch vision, it returns a three-dimensional array. Image.shape. The first even though the images are grayscale, so they have just one channel, so it's kind of just a matrix with two dimensions, height and width. But because we're using torch vision read image, it creates actually additional dimension for channels. And here we have just one channel gray. But to visualize um, this function, imshow uh, expects the channel dimension as the last dimension. So that's why we changed uh, the order of the dimensions. So we use permute. Permute will place zero channel at this position, at the last position. So the also you see here division by 25, because if we look at the data, you can see the format is 8-bit format, so numbers from zero of the intensity from 0 to 55. But in neural networks, so there's another format for images, which uses for intensity range between 0 and 1. So to cast into this format, we can just divide by 255, and we will get the range between 0 and 1. And also, next time when we will talk about batch normalization, I will explain why neural networks uh, work better with smaller values, not with large values. So it's the standard preprocessing to make the range between 0 and 1 instead of integers between 0 and 255. Yeah, and if you don't use this grayscale, uh, the visualization will look like that. So if you know that your image is grayscale, you should use this CMap grayscale, and it will look like as it should look like. Okay, let's indicate our directory, mnist png, and I will use library which is called pathlib. It helps to traverse your folders. So in pathlib, we can create this class path equals with this class path. And for example, we want to read all the paths to only to images, because in our folders we can have other files like text or I don't know, PDF. So we can create list of paths, list um, paths list as list of paths, and use these regular expressions R globe. So it will search for all the files ending by .png. Of course, you can use OS library built in as well. So it returns a list. So this is how the first element of the list looks like. You can see it has its own data type, POSIX path, and this is the path to the image. And this is actually the label. So this image is the image of um, digit one. So to get the string, we should use as pos x, then it will return a string. And here's my dataset class. Now you will understand this code. Uh, we initialize this class with path to our images. Then we create this pathlib class. We create the list of the paths to all the images in this folder. And then length returns the length of this list. And get item, you remember the input is index, and we return an image. So to return an image, we use read image, and we read the path from our list of paths. So as POSIX just to get the to the string. And we divide by, because it returns tensor, it adds extra dimension. So we use squeeze and we divide by 255. And for target, we should parse our string. So we should get this number as the label. So I'm just using split, split by slash, and take the second from the end element. And let's initialize this data class. You remember we have train data and we have validation data. Okay, I think I have something wrong here because, yeah, I believe here I should add train because otherwise I will read all the images in my folder, and my folder contains both and train and validation. Okay, we create the data set. Again, when we run this code, it will create the list of paths to the images. And you can do the same for any data set of images. Just upload images in one folder and then read the paths to the images. And here we read the paths to validation set, and we create. So you can get an image now by index, for example, train data. Oops, train data of 0. It will return you the torch tensor with scaled pixel intensities and the label tensor. Okay, after we created the data set, this was the most difficult part. The rest of the code will repeat our previous code, because to create the data loader, we just use the dataset class and indicate the batch size and shuffle true or false. As you remember, for training, we use true shuffle. For validation, there's no reason to shuffle the data. After we created the data loader, it will split the batches. Let's look at the output. It will just split the, in my case, 64 random images. And 64 labels for these images. Okay. And now, yeah, I import an N module and optimizer. You remember Adam is default optimizer. It's interesting, we don't have any Adam in our class. Um, and actually, in other sections, I don't have Adams. Okay, I had just a neighbor, Adam, last year. So, and we should build a model. How can we build our model if our data is two-dimensional, 28 by 28 pixels? The approach that we will use this week is to um, put this data into long array, which is called flatten. So there is a layer which will actually um, convert your image into array. And then we can work with vectors, just as before with multidimensional arrays. Okay, so I'm using here sequential. So first step, I apply flatten. Um, if so, for example, if I apply flatten here, mm, and dot functional dot uh, flatten. Um, uh, just an n flatten. So there is an n and an n functional. The difference is that if you want to create the instance of the layer with an n layer, and an n dot functional actually returns the function, the layer as a function, so you don't need to create the instance of this layer. But it looks like flatten is it's not a it doesn't contain any parameters. It just changes the shape of your array, so we can use just um, an n dot flatten. Um, let's see. Okay, torch. Okay, so we can just use torch flatten. And now, oh, it also flattened the batch size. Because I want to have the same batch size, but image is flattened. Let's see if there is a parameter. Um, okay, we can indicate the dimension. So yeah, instead of matrices, I will have a batch of vectors where every matrix is just flattened in one long array. Okay, this is the first layer, flatten. Then we apply a linear layer that will change the dimension of input to the hidden dimension, which is HD. And after that, we apply activation. And the second linear layer and the output dimension is 10 because we have 10 classes. Okay, let's create the model. So let's initialize the model. The hidden size, it suggests 128. Okay. Um, I don't mind. And now we can apply our model to a dummy um, uh, variable model to torch dot zeros, for example. So my input is the image. Let's see, I think the first one is uh, uh, extra. So the batch size of 1 and images of dimension 28 by 28. If I use batch size of 2, I will get the output 20 numbers. So these are logits. You remember the logits um, are the unnormalized probabilities. Then we apply softmax and we will get probabilities. But so this is the output from our model, just 10 numbers. For now, our model is not trained, so these numbers doesn't have any sense. These numbers just resulted from our original initialization of our layers. So here's the important um, fact. Why I didn't apply softmax? Why I used the unnormalized outputs? Because you remember the cross entropy loss that we use for classification, it takes as input the probability of class and class label. The answer is that in Torch, if you Google Torch cross entropy loss, so the criterion computes the cross entropy between input logits and target. So uh, the cross entropy loss in Torch applies softmax inside this cross entropy loss function. If you use TensorFlow, in TensorFlow, it doesn't apply cross softmax. So in TensorFlow, you should apply softmax before cross entropy loss. In Torch, you should use the raw outputs from the linear layer. But for binary cross entropy, for example, for your homework, you should use binary cross entropy because for homework, you have data set on the plane with two classes. I believe for binary cross entropy, you should apply a sigmoid function. Let's double check. Torch BCE loss. Oh, actually, there are two different loss functions. One BCE loss, which expects the input probabilities. So you should apply sigmoid function before BCE loss. And also BCE with logits. So in this case, you don't need to apply the um, sigmoid function. Cross entropy between target and input probabilities. Yes. So for your homework 10, you will use BCE loss, cross entropy loss. So your final layer in your model should be sigmoid function. In my case, or you can in homework you can do also the output dimension 2 instead of dimension 1, and then apply cross entropy loss instead of binary cross entropy. If you will use binary cross entropy loss, your output dimension should be 1 and sigmoid function. But you can use output dimension 2 and then use cross entropy, but for 2 classes. Now we will use for 10 classes. Okay, let's create a criterion. And cross entropy loss. Okay, and optimizer is Adam. We pass model parameters. Learning rate is by default negative power of 3, so you can just pass the parameters in your optimizer. And training loop for epoch. Actually, I can just copy paste from my previous code because now, after we created the data loader, the rest is will be the same for any deep learning project. So we can just copy paste this training loop. Um, and in my data loader is called train, I believe data loader, train data loader. We read axis, we read targets, then we calculate predictions, which is 10-dimensional vector. Then we apply cross entropy loss, calculate backward gradients, update our parameters, and zero gradients. And writer, okay, I didn't create writer. Let me create writer next time. For now, let's just use because I also want to create another the validation loss function. But let's do this next time. For now, let's just train our model and see how it performs. So let's use history for the loss and train for 100 epochs. Okay. And alpha 0.95. Okay. Visualize our loss. And then I also want to look at the accuracy. The MNIST dataset is balanced, so it has 50 images for every class, so we can apply accuracy as the metric. So to calculate accuracy, I will need to make a prediction. So y spread model forward, but because model returns just 10 numbers, I should also take argmax of this torch dot argmax alone dimension with -1. Let's see. And then I will compare this with true labels. So my predictions are just real numbers. Argmax will return the index, and index in our case coincides with actually a digit number. So that's why I just apply argmax, and I can compare this with true labels. What are the true labels? Um, oh, actually, I should write a for loop for in validation data loader. And you can see the model now is bigger and data set is larger. So it's training. Maybe I can stop training because maybe 5 epochs would be enough. I don't know. I have 100 just left from previous absolute value function. Um, yeah, let me stop training because I believe actually the loss went pretty well down. And now you can see also like how smooth loss looks better than not unsmooth loss. So now for X in batch, um, yeah, let's see my code for evaluation. Um, oh, I should create the array where I store the values. Um, okay, let's do just for one batch, and next time we will evaluate for the entire validation loss. So for we calculate predictions. Um, let's print these predictions and true labels. Oh, okay. Because my validations data loader is not shuffled, it returns in the order. So all the ones. Let's look at the train, for example. Yeah, in train, we can calculate the accuracy. Mm, and for out data type. Um, okay, maybe I should cast the data types. Okay, but I think you understand the idea. Now we have the output from our model, predicted values, and the true labels. And we can compare these outputs and calculate the accuracy. Um, on so in your homework, you should get accuracy about 95% with this simple model. And next week, you should get about 97 or 98 or 99 with convolutional. And the human accuracy on this Venice data set is 98%. So next week, when we will talk about convolutional neural networks, actually, it was the first model which actually beat the human performance. And this is the beginning of the 2005, if I'm not mistaken. And this is the beginning of the era of deep learning, actually. This was the first model built by Jan LeCun that outperformed the human digit recognition. Okay, let's stop here for today and finish this next time.